Hello, and welcome to this Radiant Vision Systems webinar. My name is Matthew, and I will be your GlobalSpec moderator. With us today is Eric Eisenberg, the Optics Development Manager at Radiant Vision Systems. And Eric, welcome to today's event. And with that, I will pass things along to you to get started.
Great. Thank you, Matt. Welcome, everybody. Okay, so first I'm going to introduce Radiant Vision Systems. We specialize broadly in light and color measurement, and we have been designing and manufacturing scientific-grade automated measurement solutions for 30 years. We support a global customer base from the Americas to Europe to Asia. Today, I'm happy to share our expertise in optical testing and give you a look at our latest solution for measuring XR displays. Today's presentation will cover the characteristics of a fundamental XR measurement system, persistent challenges for measurement where test systems are needed to address optical design diversity in terms of various display fields of view and pixels per degree, headgear and device form factor, dual eye visualization scenarios, variable focus scenarios, and other unique measurement parameters. We'll introduce Radiant's new solution, the XRE lens, which provides a more flexible optical component to solve these challenges and address a wider breadth of in-headset measurement scenarios. We'll give examples of the XRE lens software and discuss benefits for fully automated testing. And finally, we'll summarize Radiant's available solution options and the product specifications. To get started, let's discuss some of the characteristics common across XR measurement systems. These system designs address basic visualization parameters of all XR headsets. All test systems used for XR display evaluation must account for visual elements produced by the device as perceived by the user. We'll refer to the XR display as the composite visual elements produced and transmitted by integrated displays, projection units, and associated optical modules within the device. Visible light is the medium by which every display is perceived. The quality of an XR display is dependent on the user's perception of the light relayed to the retina from the display and the optical elements in the device. Evaluation of light and user perception are key elements to address in our testing. User perception is influenced by parameters under which these displays are viewed, which is near to the eye, within a headset, and across a specific angular field of view. XR display test systems are designed to replicate the viewing conditions of the user as much as possible in order to ensure accurate qualification. Measuring light based on user perception requires photometric and/or colorimetric principles. Imaging photometers and colorimeters have long been applied for electronic display measurement and in recent years have been adapted for XR display measurement. These systems incorporate universal functions, optical filters, and formula to match their spectral responses with that of a standard human observer. This means they quantify visible light at the same intensities per wavelength as the human eye does. Here's an example of a radiant imaging colorimeter. Color filters on an internal filter wheel each represent a curve on the CIE color matching function plot. This plot, shown to the right, with solid lines describing the standard human visual response. On the dotted lines, the response of the radiant imaging colorimeter closely follows the CIE curves, meaning the system is capturing highly accurate values of light and color that reflect human perception. Like the human eye, a measurement system must also visualize the display in a spatial context, capturing the entire field of view at once. Along with photometric principles, imaging is a key element for testing, which is why imaging photometers are the fundamental camera component of an XR display test system. These systems measure brightness or luminance and color or chromaticity and characterize properties derived from context by comparing values across an image. These include uniformity, which could be uniformity of the luminance, the chromaticity, or even the focus, as well as overall contrast, distortion, the MTF of the display modular transfer function, the occurrence of and location of defects, and other qualities. Here we can see common analyses applied to measurement images of an XR display, captured with a photometric imaging system. Across devices, XR display measurement routines will include various combinations of these common display tests. Okay, the angular FOV, or field of view, is also important because XR devices display virtual images in angular space. This creates an immersive viewing condition that emulates the human visual field. The imaging lens of the display test system must therefore capture values at angular positions to measure virtual images as they are seen by the user. As shown in this illustration, an imaging lens must accommodate narrow to potentially wide fields of view to address current devices. We want our imaging system to capture the field of view visible to the human observer, which can be immersive or fairly wide. For this reason, a wide field of view lens is a common requirement of an XR display system. A final commonality of these test systems is the ability to match the user's eye position inside the headset. Here, we define in-headset viewing parameters. XR displays are viewed near to eye. The headset eyepiece, or the exit pupil of the headset, is usually positioned 10 to 20 millimeters from the intended position of the user's eye, which is called the entrance pupil of the system, which is the human's visual perception. Our goal is to match the intended entrance pupil position with our imaging system's entrance pupil. In imaging lenses, the aperture acts as the entrance pupil of the imaging system. So this presents a pretty significant problem for standard photography type lenses. So while it may be possible to fit a standard measurement lens within an XR headset, it's extremely unlikely that this lens will capture the full field of view as seen with the human eye. Because the aperture of a typical imaging system, or photography lens, is buried inside the lens housing, as shown here on the right. I'll draw a circle. The lens aperture is located. So the resulting image captured by this lens will be clipped by the housing of the lens itself, because the display is beyond the exit pupil of the headset. So this is sometimes referred to as the Knothole Effect. And the closer the entrance pupil is to the knothole, the greater the field of view can be seen beyond the fence. So by bringing the entrance pupil closer to the actual exit pupil of the headset, we can effectively bring the lens closer to the knothole and not clip the field of view. So how is that accomplished? So to achieve the desired entrance pupil position, lenses used for XR display tests are designed with an aperture at the front of the lens. This way, the entrance pupil of the imaging system can be positioned at the same location as the human entrance pupil relative to the display. This enables the system to capture accurate, full field of view measurement images of the display beyond the headset exit pupil. So while these commonalities drive essential elements of XR display test systems, the devices we want to test are incredibly diverse. In order to replicate human vision inside unique headsets, manufacturers are often required to invest in costly, customized equipment to meet specific measurement scenarios. There is a wide array of these types of devices available on the market, and the specifications vary pretty significantly between the different types of devices. For instance, each XR device differs in form and function to meet particular application goals. A pair of AR smart glasses intended for daily use have reduced hardware size and weight, which typically means smaller components that limit the display field of view. On the other hand, a VR headset intended for gaming may be designed to maximize field of view and boost visualization performance with high-resolution displays and adaptive focal points, such as foveated optics. So pixels per degree, PPD, is influenced by field of view versus the XR display resolution. PPD is the display resolution visualized over the angular field of view of the display. Higher PPD increases the amount of visual detail, which typically is a goal of XR optical design, to create an immersive image. The in-display measurement, the imaging resolution applied to capture the display field of view, should exceed the resolution of the XR display itself, and hopefully greatly exceed. To replicate human vision in the headset, we can aim for a display test system that matches or exceeds what's called human eye resolution. To define what this is, we will use the standard eye chart. The visual acuity of a human eye is measured in arc minutes. 1 arc minute is the width of a single stroke of this E in the eye chart corresponding to 20/20 vision. An arc minute is also equal to 1/60th of 1 degree. Since the smallest visual element a human with 20/20 vision can see is 1/60th of 1 degree, human eye resolution in XR displays is generally accepted as 60 pixels per degree. This is sometimes referred to as the retinal resolution. An XR display test system that can discern 60 ppd, ideally more, is desirable for accurate evaluation of the display. Like XR devices, XR display test systems must balance imaging resolution and field of view to increase PPD. If we have lower resolution imaging systems, this means fewer measurement pixels to capture and discern the visual elements of the XR display. This is a bigger problem when capturing larger fields of view. Assuming we are using an imager with the same resolution, the measurement pixels spread over a larger area means fewer pixels per degree can be applied by the imaging system across the display. This is illustrated by the example here. A very common imaging system resolution is around 12 megapixels, which we'll assume is a 4,000 by 3,000 imaging pixel sensor. We need to measure a display that is 30 pixels per degree across a 20-degree horizontal field of view. 12 megapixels gives us 200 pixels per degree of imaging resolution, or around 6.7 imaging pixels to capture each display pixel. But what if the field of view of the display is larger? Applying 12 megapixels to a 70-degree horizontal field of view, the measurement system achieves only 57 pixels per degree. Not only is this lower than the human eye resolution, but it results in a little under 2 imaging pixels available to measure each display pixel. A high-resolution imaging system is really needed in most cases to ensure that the measurement system is comparable with human eye resolution of 60 ppd, and that it exceeds the ppd of the XR display. The trouble is that many XR display test systems rely on relatively low-resolution cameras like these. These solutions also don't provide resolution optics. For instance, choosing a camera with more megapixels, in this case where it's needed, for instance, when we have to measure a larger field of view. Another persistent measurement challenge of XR displays is headgear. This includes straps, helmets, and even narrow stems of some smart glasses. These form factors leave little room for optics to enter the headset. Imaging lenses can be bulky and are usually long and straight. When headgear is a component of the XR form factor, there may not be a direct linear path from the back of the headset to the display. This can make it impossible for imaging optics to be positioned at the necessary entrance pupil position for full field of view measurement. Optical systems designed to test these headset configurations would need to be customized to fit each device, which is an extremely cost and time-intensive solution. A similar problem arises if there's a need to measure two eye positions. Simultaneous dual eye or stereoscopic measurement is often desirable to ensure the XR display appears high quality based on binocular human vision. Effectively, you want to test both displays to make sure that they're a good match, and it would be uncomfortable for each display to be different. Dual eye measurement systems evaluate changes in brightness, color, uniformity, and focus from left to right eye, which could cause visualization issues and discomfort. A dual eye test setup requires multiple imaging lenses in the headset at the same time, each achieving the intended entrance pupil position for left and right eye. Both headsets and imaging system form factors pose a challenge here. If bulky lenses are used for measurement, it's very unlikely that more than a single imaging system will be able to fit inside the headset. This is even more of an issue if head straps or other obstructive hardware are present that interfere mechanically with the measurement system. Another consideration is the ability to focus and refocus the measurement system. So it's becoming more common that XR headsets are designed with multiple focal distance for more natural viewing scenarios. For example, one focal point for perceiving elements as near and a second focal point for elements that are far away. We would ultimately like to sweep over a range of dynamic focal points which more closely matches human vision. The lower left images here show a liquid lens example where multiple focal points can be produced with a single optical component in the headset. Related to this, foveated optics are used to produce a high-resolution region as a focal point. This, as shown, is in this example from Varjo in the upper right. Here, two displays are used with a combiner to rotate the focal point. Traditional imaging systems have relied on lenses with manual focus. These lenses are problematic for several reasons. Any manual adjustment of the measurement system can introduce error. So, of course, this is an issue with manual lenses. Without computational checks and balances, manual focus may unintentionally shift during measurement. Many manual focus lenses are focused by essentially rotating the entire lens barrel and moving it in and out closer or further from the sensor. And in the process of actuating the focus, it will typically misalign the system, and then also just finding the right position can be really challenging. So if this happens, poor focus could impact the accuracy of the result. For instance, a display could fail an MTF test because it has low image clarity introduced by the poor focus of the measurement system itself. So consider the images on the right. As the display falls out of focus, the yellow edge of the shape captured in the headset becomes blurry. In a slant edge MTF analysis, this display would fail, not because the display was faulty, but simply because poor focus was introduced by the measurement optics because it was difficult to focus the manual lens. Another issue is that the lens barrel of traditional lenses changes its length as it's focused. So this changes the position of the imaging system's entrance pupil relative to the display. In this case, the imaging system would need to be repositioned whenever the focus is adjusted so that the entrance pupil is restored to the correct measurement location. This not only takes time, but increases the risk that there could be an error in the measurement setup, and this kind of setup is really completely impractical for any kind of mass production testing. So another drawback of manual focus lenses is that they make it nearly impossible to perform an effective through focus MTF analysis. So through focus MTF evaluates the focus or the quality of the focus uniformity of an XR display. So as seen in this example, several measurement regions are displayed on the device. And slant edge analysis is performed in each region. Over many iterations, the focus of the measurement system is adjusted from unfocused to focused and back to unfocused. A measurement is taken at each step or iteration to find the focal distance that produces the best focus for each region. The output data plot shows the MTF data at each focal setting for each region. So at 1 line pairs per degree, it looks like we did 15 here. So each line shows the result for a given region, and each dot shows the MTF measurement for a specific focus motor count. Simply put, there is no effective way to test for through focus MTF using a manual lens. There are too many focal distances to test. The optimal focus for each measurement region is really unknown, and each manual adjustment of the lens can significantly increase the measurement time and risk of error. It's especially true if the entrance pupil is changed with each focal adjustment. So doing this kind of analysis is really impractical without an automated focus type system. So demonstrated by these examples, we can see that the variability in XR devices is so prevalent, there is really no single measurement system design that can meet every need. We can take two devices and compare the range of parameters that impact the measurement requirements: form factor, display type, angular field of view, resolution, pixels per degree, focus, dual eye visualization, foveated optics. These specifications are completely different from one measurement scenario to the next. So even if a measurement system meets the fundamental needs for near-eye display testing, there are reasons custom solutions are still used. In these cases, a camera lens solution is engineered from scratch and designed to meet the specifications of a specific XR device. And as the optics development manager, I know that these custom systems can impose a significant time and cost burden on the manufacturer. Certainly, lenses that we've developed at Radiant have taken a long time and cost more than we necessarily had hoped. The process to design, build, and calibrate a custom optical system is time-intensive, on the order of months to maybe even years, as well as cost-intensive to cover research, development, sourcing, and equipment testing. Manufacturers really need more flexibility and greater capability of their measurement systems to support efficient and effective XR display testing, especially in unique measurement scenarios. So that's why we're here today. Radiant developed a new device. Our team here got to work to solve this challenge. Radiant designed a new optical system to enable user-centric measurement across a greater range of XR display test scenarios. Here it is. It's the XRE lens. So this utilizes a patent-pending invention that was conceived by Radiant. The lens combines readily available optical components and enables Radiant to produce XR display test solutions extremely quickly. This lens is highly flexible, capable of replicating human vision in an even broader range of XR devices. Using this system, we can address even more specific measurement scenarios without the need for costly customization. The complete solution provides multiple camera and lens configuration options on the same platform with our most advanced imaging capabilities. Let me talk a little bit about what it is. There are a few recognizable components that provide the XRE lens's optical architecture. Fundamentally, the design includes a camera and the XRE lens. The lens design combines two primary components: a reversed eyepiece and a macro lens. Examples of commercially available eyepieces include those used for telescopes, microscopes, rifle scopes, etc. Macro lenses are very common in photography. Macro lens provides the system's focus. This component structure is far simplified from a ground-up custom lens design. It is much faster to produce, prototype, and the modularity supports a few solution options. Fundamentally, the XRE lens solution is designed to enable in-headset display testing. Manufacturers have several options to tailor an XRE lens solution for their measurement needs. First, the lens has two configuration options, what we're calling folded and non-folded, to address different integration requirements. For instance, in dual eye measurement, where two lenses are simultaneously positioned at each eye's pupil position in the headset, All configurations offer electronic focus, which enables focus to be controlled via the software. And the lens can be paired with a prometric imaging system of choice, a colorimetric or photopic system, depending on the need for the color measurement, imaging resolution options up to 61 megapixels, and fields of view of up to 35, plus or minus 35 degrees, or a full angular field of view of 70 degrees total. Following the fundamental expectations of an in-headset measurement system, the XRE lens solution ensures evaluation of the display as perceived by the wearer of the headset. As we discussed, requirements for replicating the human visual experience include measurement of visible qualities of light perceived by the user, spatial imaging replicating the human visual field of view, capturing a wider angular field of view, and an entrance pupil that matches the human eye position in the headset. The XRE lens solution meets these requirements using the innately close match of the prometric camera response to CIE color matching functions, which, as we know, describes standard human vision perception and color, and of course all of Radiant's calibrations that will correct any errors in those curves. Also, the high imaging performance of prometric cameras, which are able to capture the complete angular field of view of the display at once, as seen through the headset. And of course, the system has an aperture at the front of the lens to ensure we can set the entrance pupil at the human eye position in the headset. The aperture of the XRE lens is very unique, however. That's because it's a virtual aperture. This aperture has no mechanical specification, enclosure. It isn't enclosed by the lens's hardware. Instead, it's projected in front of the lens, as shown here on the left, where we show the eye position. This is thanks to the lens's reverse eyepiece. In a standard eyepiece for a telescope, the eye position is intended to be a fixed distance or the eye relief distance from the eyepiece for comfortable natural viewing. If we flip this eyepiece image on the right, the exit pupil of the eyepiece becomes the entrance pupil of our measurement lens, just like we show on the left. A virtual aperture is advantageous because it can fit in more positions to replicate the human pupil in the headset without mechanical interference of the lens's housing or enclosure. For some headsets, a front-located aperture that sits inside the lens, even by a few millimeters, has been problematic for some applications we've supported. The mechanical hardware may prevent the measurement system from being positioned at the appropriate near-eye location. Let's say we have a VR headset with an eye relief distance of 12 millimeters. We want to test the visual quality of the display as seen from this distance. We'll assume that due to hardware and fixturing constraints, we can only get our lens so far inside the headset. Let's assume that the mechanical position of the lens puts the end of the lens only as close as the 12 millimeter eye relief distance. Using a lens with an aperture inside the lens hardware, our entrance pupil position is always just a little bit farther back, whereas our virtual aperture can be much closer and exactly where it needs to be. Even with 2 millimeters worth of hardware in front of the mechanical aperture, the entrance pupil is now 14 millimeters away from the exit pupil of the headset, unable to reach the eye relief location. The XRE lens's virtual aperture extends out from the lens hardware, giving us more range to work with in placing the entrance pupil at the appropriate position. There are other ways the XRE lens solution goes beyond fundamental capabilities for in-headset testing. To meet the need for higher measurement resolution, XRE lens provides several options to meet and exceed human visual acuity of 60 pixels per degree. Manufacturers can choose to pair the XRE lens with a high-resolution imaging system offering 29, 45, or 61 megapixels. Based on the lens's 70-degree horizontal field of view, an XRE solution can achieve 58 to 100 pixels per degree. The XRE lens isn't Radiant's only display test solution. In fact, we have a 120-degree field of view. We have a 120-degree field of view in our original ARVR lens, which was a fixed focus lens that was manually adjustable. Pairing this lens with a 61 megapixel imager, by virtue of the sensor specification, we can achieve 80 sensor pixels per degree across the field of view. So why would you want to use a lens with a narrower field of view? Applying the 61 megapixel resolution across 70 degrees with the X-ray lens, we get a little bit more, 85 pixels per degree across the display. This increases measurement precision when needed. For example, AR and MR devices typically have smaller fields of view. So if we can narrow our imaging field of view, more sensor pixels per degree can be applied and are useful for the imaging application. This is also a consideration for foveated rendering, where a small area of the display may require greater measurement precision. As a general rule, in imaging, smaller fields of view are associated with higher spatial resolution and clearer images. Considering this, a narrower field of view can increase the accuracy of results for characterizing qualities like MTF or focus quality, which rely on image clarity for accurate measurement. In these cases, manufacturers can apply the XRE solution to test displays with the increased accuracy. This is an example of what we see in our software. Here, we're measuring about plus minus 35 degrees, around 70 degrees total. In the right image, as we zoom in on a projected element, we can see we're getting very high resolution over the measurement image area, offering us greater precision for this slant edge MTF analysis. You can even see some of the pixels in the display. Another hallmark of the XRE lens is that it offers different optical form factors to fit any integration space. A folded lens configuration is made possible by adding a fold mirror to the design. In this configuration, light from the display enters the eyepiece, is reflected by a fold mirror in the lens, which adjusts the optical path 90 degrees, and then it is directed toward the imaging system's internal sensor. Now, we can fit our measurement system inside any headset, avoiding head straps and surrounding headgear, and put our lens's aperture at the appropriate entrance pupil position. Folded optics also provide new integration possibilities because they offer more angles of approach to the imaging position. For instance, we could feasibly fit two XRE imaging systems within a headset at the same time to perform simultaneous measurement of the left and right eyes. Here, we show two folded configurations coming from the top and the bottom of the XRE device. Now, we can compare visual display quality from eye to eye. The parameters of each measurement system relative to the headset and relative to one another can be tightly controlled, and there is no error introduced by repositioning and refocusing a single system. A second benefit of the stereoscopic integration is increased efficiency, since testing speed and throughput are effectively doubled when both eyes are measured at the same time. Here's an example of what a stereoscopic measurement system software output might look like. In each window, we have captured a test image at the left eye position and the right eye position. We can use this pattern to measure focus uniformity of the display through each eye, comparing focus from eye to eye. We could also look for differences in brightness, color, contrast, and other qualities from eye to eye simultaneously. Measurement values are captured from each eye position and compared to ensure a seamless viewing experience across binocular field of view. Now to the challenge of focus. As we discussed, measuring various focal distances can be challenging for traditional lens systems, but the design of the XRE lens offers some advantages. An eyepiece and a macro lens in combination provide the focus of the system based on the f-stop of the eyepiece. Both eyepiece and macro lens are positive image-forming lenses. Effectively, the eyepiece acts as collection optics, and it produces an intermediate image of the captured scene between the eyepiece and the macro lens. I'll highlight that with a blue circle here, where the intermediate image is located. The macro lens then acts as a relay optic, and it focuses that intermediate image, relaying it onto the sensor itself. In application, when the f-stop position of the eyepiece is effectively focused at infinity, as shown in this image, the macro lens can be focused on this f-stop position to focus the entire system at infinity. To focus the imaging system at a shorter distance, the macro lens can be focused on this intermediate image plane located behind the f-stop of the eyepiece. So effectively, we make small changes in the focus setting of the macro lens, which result in relatively large changes in the focus of the overall system. So in every case, the imaging system would be focused on the virtual image in the headset as seen at the perceived distance requested by the software. So we know that manual focus lenses are problematic when adjusting to different focal points. In Radiance XRE lens, the macro lens eliminates this issue because the macro lens is designed with internal focus functions that does not increase the overall length of the system or change the position of the eyepiece while refocusing. So refocusing doesn't require repositioning of the imaging system to the entrance pupil position prior to capturing a new measurement. This reduces potential alignment and focus errors, and because the lens system can remain stationary and unchanged during the focus adjustment, automatic electronic focus can be effectively utilized. In an electronic focus configuration, focus settings of the XRE macro lens are set and controlled via software. Thanks to this electronic control, the optical system takes very little time to set up and can also adapt to new virtual image distances on the fly using data from the image analysis software to set the appropriate focus automatically. Electronic focus also enables effective through-focus MTF analysis. Using image analysis functions, connected measurement software can iterate through the focal settings of the electronic lens until best focus is found for each analysis region in the measurement image. So since the pupil position of the optical system doesn't need to be adjusted for each focus setting, the through-focus MTF analysis can be run completely autonomously without any intervention from the user or the operator. A complete through-focus MTF test can be done in a matter of seconds. In this example, the XRE lens system has run over 30 focus settings at each measurement region to find the best focus result at around what we're saying is 3560 motor counts. And in the commercial system that we are releasing today, the motor counts are all calibrated to actual physical distances. True focus MTF testing is really valuable for ensuring the quality of a focal region, like those used for foveated optics. In cases where two displays are used in the headset to create a focal region, basically we need to measure both displays. The focus display could be easily tested for through-focus MTF based on the automated electronic focus of the XRE lens. Another benefit illustrated here is a unique use of Radiance pattern generator in our TT ARVR software. Dual display testing requires that we push test images to both screens so the measurement system can evaluate the performance of each display separately or together. In the latter case, we are testing the resulting composite image just as the human would view it through the headset. In this solution, we can interface between the measurement system and the headset to control both displays independently. The analysis software can facilitate side-by-side or composite analysis to look at the properties of each display and their effects on foveated visualization. So effectively, some of these displays really require a number of video inputs, and we've developed a device interface, a pattern generator, that can produce effectively as many video signals as required by the display's specification. So that's one example of the XRE lens software capability, but there are many more. The TT ARVR platform provides a lot of power for display analysis as well as fully automated testing. So Radiant developed its Truetest ARVR software with analysis and functions most relevant to XR display measurements. Analysis in the TT ARVR software platform include luminance, chromaticity, uniformity, contrast, distortion, focus uniformity, modular transfer function, line pair, slant edge, or LSF version, true focus MTF, mirror and defects, warping, and display field of view. The software not only controls the functions of the connected imaging system and XRE lens, but also the test images that are pushed to the XR headset. As an image is shown on the headset, the software initiates a measurement by the imaging system and synchronizes an analysis of the captured image. The software can run the analyses asynchronously, so that allows it to process measurement results at the same time as it's capturing subsequent images in the headset. This pipelines the process and maximizes speed when testing multiple qualities. Using custom tolerances, the software can also output pass-fail results. Because TT-ARVR is meant as an automated visual inspection platform, the software also offers a built-in API and SDK for integration into automation fixtures and control systems. Here's an example of the TT-ARVR software interface. This measurement image shows that our imaging system has captured a display about plus or minus 35 degrees across. We've set up an automated measurement sequence on the left, which defines the test patterns that the software will push to the display and the analyses that will run in sequence with those patterns. Hitting the Run Sequence button automates the whole process. The software steps through each analysis and ultimately evaluates the display over all parameters in a matter of seconds. Here are some examples of measurement images captured by the XRE lens and TT-ARVR software using an actual XR headset. As we've described, each measurement image has a unique test pattern to facilitate software analysis. In this example, the tests we've run are anti-brightness, distortion dot grid, distortion line grid, MTF line pairs, the MTF slant edge analysis, and focus uniformity. Here's an example of one of the analysis in detail, slant edge MTF. Radiant developed this analysis using criteria from the ISO 12233 standard, which specifies a process for measuring resolution of electronic still imaging cameras. In our case, we use these same principles to measure the clarity of images seen through the optical system like an XR device. MTF measures the spatial frequency of an optical system. It can be thought of as a measure of the resolution combined with contrast or modulation, or how faithfully the visual details and minimum and maximum intensity values are relayed from the original image to what is projected by the headset. It measures the sharpness of the focus. In a slant edge MTF analysis, we capture a rotated rectangle shown on the XR display. We place measurement regions, or POI, at the edge of this shape. We have 4 POIs total, one for the top, bottom, left, and right edges. In each POI, the software computes multiple cross-sections, aligns, and averages them to evaluate the transition across the edge. And then on the output on the right, we have plots that show the measured values along this transition. We've got the edge spread function, which is the cross-sections that are aligned and averaged. The line spread function plot, which is the derivative of the edge spread function, and then finally the MTF, which is the Fourier transform of the LSF. So the MTF plot on the bottom includes data from all 4 POI, and this shows the actual MTF based on the angular frequency, line pairs per degree, across the transition. And you can see some noise on the right side of the LSF. That's because of the pixelization of the display itself that's being picked up. And you can see a pretty sharp frequency out at about 20 here that is showing up in the FFT. So really the MTF plot of interest is the curve on the left. Because TT-ARVR is an automation platform, it's extremely useful for production applications. For manufacturers looking to enable more streamlined manufacturing options, the flexibility of the XRE lens also provides several test equipment integration possibilities to enable fully automated inspection, folded and non-folded optical configurations to fit a range of fixturing needs, completely hands-free electronic focus for automated testing of multiple focal points. Automation routines via software can control the XRE solution in sync with test images on the headset. Also, interfacing with robotics and manufacturing control systems. Here we show a rudimentary example based on automated actuators. This configuration could be adapted for dual eye measurement and a number of test criteria. Because the imaging system measures the entire visual field of view at once, and we can automate the full test sequence, a complete in-headset evaluation can be done in only a matter of seconds. The optical test system, of course, is just a small part of the overall manufacturing engine. In order to provide information for other processes, the test system needs to be integrated in some way. Central to the test system automation and communication is the software. Our TT-ARVR software is shown in the middle here. We can use the software's API to talk to all kinds of equipment. The software pushes test images to the headset and synchronizes measurement functions of the camera. In production, these functions may be further synchronized with test fixtures and robotic positioning. Receiving data back from the camera, the software calculates measurements and evaluates images defined against pass-fail criteria. All data is output to the Central Manufacturing Execution System, often called the MES, and commands are reported out to other operations. This network requires plenty of expertise, but Radiant's measurement solutions are geared to support production testing, test pattern generation, headset display control, camera function, and test processes are all run using automation in the Radiant software. TT ARVR software supports a range of programming languages for its built-in API, and we have an extensive support network across the world that's very experienced in integrating our test systems into all kinds of different factory environments. All right, before we wrap up, I'd like to summarize the solution options that Radiant has made available with the XRE lens and their specifications. The complete XRE solution consists of a camera, lens, and software. The same fundamental platform underlies each system, which includes the Prometric imaging system and TT ARVR software. However, there are several ways to tailor a solution to meet specific needs. The XRE lens solution is designed to provide manufacturers with the flexibility to meet unique measurement parameters of their device, reducing the need for customization. These are the available specifications we have discussed. First, you have your choice of folded or non-folded optical configuration of the XRE lens. This lens can be paired with either an imaging colorimeter for color measurement or an imaging photometer for brightness measurement only. Each photometric imaging system comes in several resolution options with a choice of 29, 45, or 61 megapixels to ensure optimal pixels per degree, and every XRE solution comes with electronic focus capability, a full angle field of view of up to 70 degrees, and works with TT ARVR software for rapid automated testing, whether in R&D or production stages. The high flexibility of the solution is designed to eliminate the need for custom designs. Our goal is an effective and efficient solution that covers a range of measurement scenarios, ultimately saving you cost and time to deploy for testing. The last thing I'd like to share are the technical specifications of the XRE lens shown here. These include folded and non-folded configurations paired with Prometric imaging colorimeters and photometers in 29, 45, and 61 megapixel resolutions. Our system's focus can be electronically adjusted from half a meter out to infinity. We've specified a minimum interpupillary distance, or IPD, of 63 millimeters for dual eye measurement setups. And for each system, we are achieving less than 0.02 sensor pixels per degree resolution. We have previously talked about this specification in pixels per degree. In terms of pixels per degree, these systems offer 58, 100, and 85 pixels per degree from left to right. Okay, so let's wrap up today's presentation. With so much diversity among XR devices, there's an increasing need for measurement solutions to exceed the fundamental requirements for XR display evaluation. Photometric imaging, angular field of view, proper entrance pupil position are not enough to continue to replicate human vision in each device. Until now, camera lens systems have not offered the flexibility to address unique measurement parameters requiring manufacturers to invest in costly custom solutions. Now, with the XRE lens, we can better replicate human vision in a range of headsets, meeting more parameters out of the box with folded and non-folded optical designs, high-resolution camera options, electronic focus, dual eye measurement capability, fully automated testing, and integration capability to production systems. The result is a solution that enables manufacturers to continue to replicate human vision for accurate XR display testing, while significantly reducing cost, time, and complexity to deploy an XR measurement system. The XRE lens solution offers significant capability on a single platform. So thank you for joining the presentation. So we're going to move to the Q&A session now, but if you need to leave or have any questions, please reach out to the email and website shown here. Otherwise, I invite you to stay online and submit your questions, and I'll do my best to answer as many as I can.
Excellent. Thank you, Eric, for that great presentation. And to the audience, as Eric mentioned, we're now moving into the Q&A session. You still have the ability to send us your question by entering it in the Q&A box and clicking submit. Okay. Oh, wow, there's a lot of great questions in here. Okay, here we go. Here's the first question from our audience. Is the vertical field of vision also 70 degrees? Eric?
The answer is yes, Matt. Basically, in the past, for the ARVR lens that we had designed previously, the image circle overfilled the sensor, And with this design, we are containing the image circle fully within the sensor. So we do have 70 degrees full field of view in all azimuth directions, as long as you're using the largest sensor, which is the 61 megapixel sensor.
Great, thank you for that. And next question from the audience. Can you explain how the focus settings can be automated?
It's really simple. So basically in the software, there's a measurement setup that has a field where you enter the focus distance. And so you can type in any number from half a meter out to infinity. And the lens is calibrated to automatically set the focus at the distance that was requested. And it's also possible to iterate that focus through different positions so that you can find the best focus, just like we're showing with the Focus MFT.
Okay, let's see what we have next. Okay, here's a great one. So first, starting out with thank you. Thank you, we're glad that you're here, and all praise goes to Eric, of course. And here's the question. Would you please introduce me more about dual eye measurement? How can one lens do the simultaneously measurement for two eyepieces?
Sure. So the reality is that you really need two lenses for the two eyes. So for the stereoscopic measurement solution that we showed in the presentation, and let me just pull up the picture of the concept here. Basically, we have two imaging photometers side by side, each with an XRE lens attached. And we have this interpupillary distance of 63 millimeters that we specified as the minimum. So as long as the displays can be placed 63 millimeters apart from each other, then the mechanics will allow us to place the two camera systems and lenses side by side so that we can image both displays at once.
That's great. Thank you for that. Okay, moving on to the next question. Okay, here it is. Is it possible to customize the folded lens to be rotationally 90 degrees from where it is shown?
I would think so. You know, we've shown the designs that we have here, and there's this bracket, and again, that you can see in this slide here. Let me just highlight that. This is designed to give you a nice reference position to be able to align the system to your device. Everything is based off of the brackets location, and you can use that as a datum. But there certainly would be options for specific requirements based on the customer need.
Great, thank you. Okay, moving on to the next question from the audience. If we want to test the MTF at human eye resolution, what is the minimum requirement for the PPD of imaging systems?
It's a really good question, and it's not always really easy to answer. The MTF of the imaging system itself needs to be taken into account, and we do have that characterized, and we can share that on a kind of need-to-know basis if you want to reach out further. But as a general rule, for imaging systems and measuring displays, you typically want to have 2 or 3 pixel size squares per pixel. Again, really depends on the application. So let's say that you're looking for like dead pixels or stuck pixels or something like this, or you want to do something like demura where you're trying to correct all of the display pixels so that they become uniform. Obviously, the higher the resolution you have, the better. But often we're able to get away with sort of a 2 by 2 sensor pixels per display pixel.
Nice, thank you. Okay, and here is our next question from the audience. PPD was shown as 100 for 45 MP and 85 for 61 MP. Why doesn't PPD increase with increasing resolution?
Sure. So the reason why is that the form factor for each sensor is a little bit different. So the image circle is fixed from the system, and then we put that image circle on these different sensors. And so some of the sensors are kind of a better match for the circle as far as the aspect ratio of the sensor is concerned, and others are not as good of a match. So you know, we clip the image circle down to where the vignetting of the system is tenable for our calibrations. And that's where we get this plus minus 35 degrees. And then when we superimpose that circle on the sensors, the different types of sensors basically are able to achieve different levels of resolution with that particular circle.
Excellent, thank you for that. Okay, and here's our next question. I think you mentioned Radiant also has a solution with a wider field of view. How large is it?
Yeah, so the standard ARVR lens can do plus or minus 60 degrees, so 120 degrees full angular field of view. And it's worth mentioning that the XRE lens that we're releasing today is the standard configuration that we plan to support and sell and test extensively. But this technology can be utilized to build different types of specific systems. And we've prototyped a number of different eyepieces combined with macro lenses. And we've tested eyepieces up to 120 degrees full angle field of view as well.
Great, thank you for that. Okay, we're going to try to slide one more in, maybe another, we'll see. Here's our next question from the audience. Does Radiant also provide a specific chart or pattern design for TT ARVR? And can customers use their own chart and pattern?
So the answer is yes to both of those questions. So the TT ARVR software comes with a number of built-in patterns that we know are very compatible with the specific analyses. Like the slant edge MTF analysis, we can display the tilted rectangle. The line pair MTF, we can display a series of lines. But then we also have what we call a bitmap pattern, which is basically just a bitmap that the customer supplies that can be pushed out to the display. And we've worked with a number of different kinds of displays. Sometimes it can be kind of tricky to take direct control of the displays when they're in their consumer electronic mode. But we've developed a number of different tools that we've used internally and with support with our customers to help push those patterns out to the displays.
Great, thank you for that. Okay, and we have one more here, so we're going to try to slide this in, and here it is. Is there any way to catch the color dispersion for AR sets?
I think so. There's a couple options. What we've shown here in the presentation today is the XRE lens combined with our standard prometric imaging colorimeter. Radiant is working on another device, which is the imaging colorimeter, but with basically a built-in spectrometer. And so the spectrometer will have a specific point of interest that it can capture a spectrum from that we can use to generate extra information, whether that be a super precise calibration of the color so that we can be extremely accurate in reporting that, or reporting back the wavelengths that are being seen, or those kinds of specific things. So, you know, the analysis can measure chromaticity. We can measure the chromaticity of different specific points of interest. We can measure the color uniformity of the display. So I think there are a lot of different options for how we could theoretically find a way to quantify the color dispersion.
power interface connection for the device. It will be a problem when using with a folded lens. What do you think?
I guess it really depends on the form factor of the display, but the folded lens is designed to, basically be smaller than the human head, which would theoretically be going into the device. So my expectation would be that it should fit.
And so we are going to wrap things up right there. So Eric, thank you so much for the great presentation. And again, thank you for taking the time to attend this webinar event. Take care. We'll talk with you.